Hey everybody, this video is going to go over a few different parts of the first project we'll have in this class. It's on synchronization and using threads and semaphores together to solve some various synchronization problems. I'd recommend you first read through this entire document. It has 4 different main parts and then some specifications for a report you need to write. But the main coding issues are these first 3. They're all the different synchronization problems, and then the 4th is accepting command line input so that you can run one of these 3, and also making sure that the command line inputs are validated so that the program won't crash or anything if incorrect ones are entered. So the first one I'll start off with is dining philosophers. You see we have the task 1 summary right down here. After reading this, you'll see that we give you the algorithm here. It's not too complex. They need to sit down, try to pick up their left chopstick by acquiring a semaphore, pick up their right one by doing the same, eat for 3 to 6 cycles, put down their chopsticks, think for 3 to 6 cycles, and if all the meals have not been eaten, you go back and you loop through. So your loop condition is to keep running this code in parallel until there are no more meals left. A few things to note is that the chopsticks are represented as binary semaphores. So a semaphore that will only have 1 permit to start and is only going to have 0 or 1 permits. The reason for that is, for example, if we pick up the left chopstick, having 1 permit on a semaphore that represents the left chopstick, it means that we can pick up that chopstick by acquiring the permit, and having 0 permits on a semaphore means that that chopstick is in use or has been grabbed by a philosopher already. So this can lead to some issues with deadlocks. If you can consider all the philosophers sit down at the table and they all get put on the processor to run just the code to pick up their left chopstick, they get switched off before they move on to trying to pick up their right. You can run into a deadlock in that example where everyone is holding on to their left chopstick and there's nothing to anybody's right, so the program just halts. So coming up with something clever here can be a good idea. Try to stop these deadlocks from happening. If you have any questions on what's allowed, I guess, feel free to reach out to us and we'll clarify anything or any ideas you have. Other than that, you'll notice that we eat a specific amount of meals. So this algorithm, these parts, you'll notice the go-to 2 here. This is a loop where we'll be eating until there are no more meals left. So multiple different threads will have access to the count of meals. You'll need to protect that variable that represents the count of meals with a semaphore to make sure that no 2 threads can access it at the same time. You don't want one changing the value while one just read it and now it has incorrect information. So we can use a semaphore, a mutex, to be able to keep that safe. Other than that, the main thing I think might be a bit more ambiguous and not as spelled out as the algorithm here is that we have a requirement for a barrier. And this is the part that I think will be good to look at and give you a good starting point, because it's the first thing that technically happens and the last thing that happens in this dining philosopher simulation. So I'll go over some code to show you how a barrier works, how you can make threads wait to execute some code until they're all there and ready. We'll move on to that right now, and then we'll go into the post office and readers, writers, and command line arguments. Okay, so now we're going to look at the code that implements a simple barrier. You'll notice this is just a Java program. We've imported the semaphore class from util.concurrent, and we have 2 classes here. We have our main class with our main method, and we have a thread class, it extends thread, called it test thread, and this is where the barrier logic happens that will run in parallel in this overridden run method. So we're going to walk through this line by line and just talk about the logic behind how this barrier works and how we can halt threads until all are ready to do something. So starting in main here, just like in our homework we did with the shouting threads, all this is doing is creating 5 threads, passing them a unique ID starting at 0, going to 4, and then starting all these threads. So very simple in main, we're just creating and running 5 different threads. In the test thread class, we have a few variables. We have a constructor that just sets this thread's ID to the ID we pass, and then we have the code that will run in parallel for all 5 of these threads. So first off, I'll bring your attention to these 3 static variables. It's very important to remember that static in Java means this is a shared variable of the class. So I can have 20,000 instances of test thread, there will only be one instance of each of these three, and all instances of test thread, all objects of type test thread, they can edit and view these three variables. On the other hand, you'll see this ID is not static, so this is unique to every thread. So every new object we create will get its own ID, but it will share these three variables. Now these three variables are, first, a static semaphore called the barrier sim. This is what's going to act as our barrier. This is what will stop threads and not let them pass and continue executing code until all are ready. So you see we start this as a new semaphore. We start it with 0 permits. The next thing we have here is another semaphore called count mutex. So we have a variable count here, it's just an int, and then we have a count mutex, which we want to have mutual exclusive access to this count variable. So only one thread should be able to see and edit and change it at a time. So with that, we just create a new semaphore with 1 permit. That way it'll only have one thread can access it, look at count, and then release its permit back. The reason these are shared is important because if, for example, they weren't shared, if these were just public or not static, there would be a new barrier sim and a new count mutex created for every thread we have. We don't want that. We want them to act on the same semaphores, so we keep these as static. So in the run method, once these 5 threads are forked from main, you see the first thing we do here in run, we update the count of threads that have started, that have arrived to the run method. So the way we do that is we're going to keep track of it in count, but because there are multiple threads that will be trying to run this code at once, we need to protect count using the count mutex. The permits are set to 1, so only one thread can acquire this. So we do count mutex, we acquire uninterruptibly. Side note, the reason we do acquire uninterruptibly is because just normal acquire will make you surround with a try catch in Java, since the thread could get interrupted while it's waiting to acquire. But adding uninterruptibly gets rid of that. So we acquire this count mutex. We increment the count. So when the first thread comes here, this count will go up to 1. And what we do need to do next is we need to see if all of the threads are here. So if all 5 threads have arrived. So the comment here says, if this thread is the final one to arrive, release the barrier permits. So if count equals 5, it doesn't for our first thread that come here, for our first 4 threads that come here. So we come to the else statement, we say thread, the thread's ID has arrived and is waiting for the barrier to be opened. After that, we release our count mutex. Since we're done looking at the variable count, we incremented it here and we do a comparison here. After that, we don't need access to it anymore, so we release count mutex. It'll go back to having 1 permit and another thread can come through and do all of these steps. After releasing the mutex on count, we try to acquire a permit from the barrier semaphore. And if you remember, we started the semaphore with 0 permits. So the first 4 threads that come here, they will be put to sleep and just sit here until barrier sim has permits they can acquire so that they can move on and continue executing code. What happens after that? We just print that the thread has made it past the barrier, but let's look at what happens when the 5th and final thread coming from main gets down here. So the 5th thread will say count mutex acquire, update the count, and it'll see that this is the last thread that's coming. So if count equals to 5, when the last thread's here, it'll be true. So we say thread, whatever thread is the 5th one to get here, is the last thread to arrive and will open the barrier. What we do next is we release 5 permits to the barrier semaphore. And if you remember, the barrier semaphore is what the first 4 threads are waiting on down here. So they're all put to sleep down here, and the 5th thread comes and releases 5 permits, so enough for all of them. After that, the 5th thread will release the count mutex, and then all 5 threads will be able to get through this barrier line and continue executing code starting at the same time. So let's see what this looks like through a run. We can see it starts off, thread 0 has arrived and is waiting for the barrier to open. So that means thread 0 came in, grabbed the mutex, incremented count from 0 to 1, skipped this if, went to the else and said, I've arrived and I'm waiting for the barrier to open. Released that count mutex and grabbed the barrier sim. Now put to sleep here. Same thing happens with thread 3, thread 1, and thread 4, but when thread 2 gets here, thread 2 is the last to arrive and will open the barrier. So when thread 2 finally got its chance to grab count mutex, increment count, it was able to check, see that 5 is equal to 5 is true, and released 5 permits, which we see in the output right after this. Thread 2 has made it past the barrier, 0, 3, 4, and 1. So we have the first 4 threads come and get stuck waiting for this barrier semaphore, since we initialized it to have 0 permits. And the 5th thread, when it gets here, the 5th thread in this case, in any case it would be the in thread, I guess, if you have in threads, we release 5 permits, in permits, so all the threads can continue executing code at the same time. So this is very similar to how the dining philosophers will not start until they have all made it, and they will not sit down and begin to try to eat until every philosopher has been or has arrived at the table. So you can use something similar to this to get that logic to work, and you'll also have to do it at the end of the simulation because all philosophers need to leave together as well. If you have any questions about this, please feel free to reach out and I can try to help you with some more examples or try to walk through it some more. And yeah, so now we're going to move on to the post office simulation. Okay, so next up is the post office simulation. It's going to be some threads modeling post office goers in this algorithm down here. It's going to loop until a certain amount of messages have been sent in the post office, like a certain amount of letters, and that's something you will get from the user. So just like in the Dining Philosophers, I recommend to just read through this first and get a general idea of what's going on, because for this one I don't have many code examples, but I do have a slideshow presentation I made about a year ago for this class, and it goes over some of my experience doing this project and hopefully can help you get started on this part in specific, the post office. So going through this algorithm, we see that when our threads start running, when our multiple people or post office goers begin executing code, they enter the post office and they first read a message that's in their mailbox. So the way that we read messages is by calling V, which is signal or release on a semaphore corresponding to that person's mailbox. So each person will have a mailbox, and calling signal or release or V on that semaphore represents freeing up space in the mailbox after we've read the message. You'll yield after that, and then if there are more messages to read, go to 2. So you'll loop through your mailbox and free up the space and read any messages that you have. After a person does that, they will compose a message addressed to a random person other than themselves. So just pick a random number based on how many threads you're simulating, and you can compose a randomly selected message to that person. To send that mail to them, you can call P, which is wait or acquire, on a semaphore corresponding to that recipient's mailbox. So putting a letter into someone's mailbox, we take 1 permit by calling P. Reading a message from your mailbox, you open up space by releasing a permit, calling V. We place the message in their mailbox, leave the post office, wait for 3 to 6 cycles, and then go back to 1. And you'll do this until the amount of messages has been sent. So it's pretty straightforward. I'm going to go over the slideshow presentation now to give you some more tips on how you can get started with a few code snippets along the way. So here we have this slideshow that I made a year ago or so to discuss some options for doing the post office simulation. I'll just put out a disclaimer here that there are many ways to do this, and this is not the right way or the best way. It's just how I did it whenever I was a student taking this class as well. And so hopefully it'll give you a good starting point and help you start thinking about ways to solve this. So first off, I just have some words that I basically just said. Anyway, the basics of the simulation. So in the post office problem, you're going to need these few things as a minimum. Again, this is just to get you started. So we're going to need a way to model these mailboxes that we'll be putting things in and out of. And we'll need one for each customer. We'll need a way to model the actual customers, the post office goers. We'll use threads for that. Then we also need a method for customers to receive and send mail, so read and write to the mailbox, and then a method to protect the mailbox content using semaphores. And in addition to the mailbox contents, you'll protect anything that's shared. So the first thing here is you should already know how to create threads in Java or C and C++ from the first homework assignment, but this just goes over how we can create a customer thread that either extends the thread class or implements the runnable interface. And here we're just looping through the number of people in the post office P, creating these customers, giving them a unique ID, and then starting. I have a note here that this ID that I give the customers in this snippet, I refer to as customer ID throughout the document. So keep that in mind, that it's a unique ID that each thread has, each customer thread has. So next up, we're going to talk about modeling these mailboxes. So like suggested in the project specs, the mailboxes can be modeled as a 2D array. And since the customers are sending their messages, I just made mine of type string, so that to write to a mailbox, I could just make an index a string selected from a random list, and to read from it, I can just output that string. So the way that you can create this is string, 2 open close brackets, mailboxes is new string p by s, where p is the number of customers and s is the size of the mailbox. These are both supplied by the user. So I'll show you kind of how this looks in like a matrix style, where we can see, so if, for this example, if p equals 2, so we've got 2 people running the simulation, and s equals 5, which means there's 5 slots in each person's mailbox. Having your mailboxes set up as this 2D array will let you index it like a matrix, like so. So for person 0 mailbox, the first index is always 0, and we have slot 0, 1, 2, 3, and 4. Same thing for person 1, except that first index goes up to 1, and we have slot 0, 1, 2, 3, 4. So as a little example, let's assume customer 0 with ID 0 wants to place a message in customer 1's ID 1's mailbox. Assuming the third slot of customer 1's mailbox is empty, this can be done by doing mailboxes 1, index 2 is a randomly selected message sent by customer and the customer ID that put the message in the box. This way I did this just so that it would be easy to output to the console. This was just following the sample output that we're given on Moodle. And later on, if customer 1 is looping through their mailbox using these indexes, should be pretty straightforward. They can simply just output print line person, their ID, reads the message, and whatever index they're on while looping through their mailbox. While you're doing this, remember to use semaphores to represent free space in the mailbox. So for example, for person 0, to put mail into there, we're going to have a semaphore with 0 or with 1. Oops. Sorry about that. We're going to have a semaphore with 1, 2, 3, 4, 5 permits to start. And as mail gets filled up in person 0's mailbox, we'll be acquiring permits from that semaphore. So say if mailboxes 00 is filled with a string, this semaphore corresponding to this row of person P0's mailbox should have 4 permits left, because there are 4 open spaces. And down here, whenever someone reads something from their mailbox, you would release a permit to represent you gaining another slot in your mailbox. So this is pretty important. I talked about it a little bit in the barrier code. I'd recommend going to this website, taking a look at all of this to review instance versus class variables, or static versus non-static variables, just because you want to be sure that when you have things like semaphores or just values that are shared between different threads, you want to make sure you're acting on the same object and not multiple copies of an object, just to make sure that there's no data dependencies or anything like that. Or sorry, data inconsistencies. So next up, we've got modeling the customer. This will be a thread. It's probably going to have a lot more variables than I list here, but think of everything that the thread would need to model a customer, and you can include that in the class, and you can specify if something's static and shared or non-static and unique to each thread. So for example, a customer ID, since this is specific to each thread, we would want that to not be static because we want each thread to have its own ID. The mailboxes, the 2D array, this would be static because you want each thread to act on the same mailboxes. You don't want a copy of each mailbox where one thread puts in mail in someone's mailbox and that person doesn't see it because it's not the same string array. And then another one, any semaphores for protecting shared variables, that would be static so that the threads will be acquiring and releasing permits on the same semaphores. Because if not, the semaphore would be kind of useless because each thread would be acting on its own copy of a semaphore. So now let's talk about an example of something that will need to be protected with semaphores, and that's the mailbox. It's kind of the biggest one here. So whenever you simulate multiple customers and multiple threads are running, you need to ensure that nothing is overwritten or accessed when it should not be. An example of this is only allow one person, thread, to access another person, thread's, mailbox at a given time. So one way you can think of doing this is having some sort of mutex semaphore that you would need to acquire before anyone can look into the mailbox. So, I'm running through the code and it's time to check my mailbox. I grab the mutex semaphore, I grab the one permit from it, and I get to check the mailbox and I release it when I'm done. So the only issue with that is while that one thread would have the mutex protecting the mailbox, no other threads would be able to add mail to someone's mailbox or release a permit if they read mail in their mailbox. So what we can do is we can have a array of binary semaphores, so one permit each, so like mutexes, one for each mailbox, where we have an array of semaphores. I called them mailbox sims, is a new array of semaphores of size p, which is the size of the amount of people in the simulation. And in this, we just create new semaphores with one permit. This true here is based on if the queue is fair, which means that when threads get put to sleep, they'll wake up in the order they were put to sleep. Feel free to use that if you'd like. But all we're doing here is creating new semaphores, one for each mailbox. And this way, we can pass this array of mailbox semaphores as a static shared variable to the customer class, and we can let all the threads of the class customer access each individual mailbox semaphore. So as an example, that's a lot of words and not a lot of code. Let's say customer 1 is attempting to check their mailbox, and recall every thread has a unique ID number, so customers 1 would be customer 1. This can now be accomplished by mailbox sims, so we index the array of semaphores protecting each individual mailbox by this customer's ID. So we do mailbox sims at customer ID.acquire. We acquire the mutex on our own mailbox so no one else can look at it. So a person can now loop through their mailbox slots and read messages, and then after we're done reading from our mailbox, we can release that same semaphore. So this way, while we're in here where the comment is, no other thread will be able to add mail or change the contents while we're reading it, but they can get every other mailbox. So if person 1's mailbox here, it's protected, like say we've acquired this first permit, while we're doing this, the other threads can check their respective mailboxes at the same time. They can read or write to them. So that's a bit of a better way to save some time. It's a little more complex, but once you get it, it makes more sense that you can have multiple threads reading their mailboxes at the same time, as opposed to just one thread having control over everyone's mailboxes. This here is very, very important. So while you're doing this with semaphores, you can run into a lot of deadlocks where, say you forgot to add a line of code to release a permit when you're done looking at something. Threads will get stuck and put to sleep at these different points in your code, and you might have a situation where you run your code, it runs for 5 seconds, and then it stops, but the code is still running, but nothing happens. To see where your threads are getting stuck, like see maybe if they're stuck at a certain line trying to acquire a permit that you never released, you can hit in the debugger options on IntelliJ, you can hit this snapshot button, and it will show you that, for example, here we have 3 similar threads waiting. So 3 threads are stuck at whatever line 131 of my program is. And we'll be able to go and see, oh, okay, it's this mutex they're trying to acquire, but I never released it somewhere, so on and so forth. Very helpful for debugging deadlocks and stuff. And the last thing is just be sure, anytime you have a shared resource, think of semaphores, because you do not want more than one thread accessing something at the same time if they shouldn't be able to. Reach out to us for any clarifications on grading or any ideas you have to work around some of these deadlocks. If you want to run them by us, we'll be happy to look at them for you. And lastly, again, just remember, this is how I personally structured the video. There's no need to do it exactly how I did. You can be creative, be clever, and come up with something on your own. But just be sure that you start early, because some of these can get quite out of hand quickly with all these different threads. But let us know if you need any help, and that's it for the post office. I'll go on to readers writers next. Okay, so for readers writers, I wasn't really sure what kind of code examples I could give that would help explain what's going on. So I figured I'd do this kind of visualization, hopefully help you see how the semaphores actually block threads from running, give you something tangible to look at and visualize while you're coding your own. And that's what this is going to be. If it helps you, that's great. If it doesn't, I apologize. And if you still need help, please come to office hours or reach out to me through email, and I'll be happy to talk through it with you or come up with some more examples, etc. So what we have here is, this is a little visualization area. We'll get back to this in a minute, but what's important off the bat is we have two different classes. We have class reader and class writer. And this here is the code that both of them run. So you'll notice the reader is a bit more complicated. That's because we do the in batches of readers. So if n equals 2, our code when it runs should have a reader read from the buffer, another reader read, one writer writes, another reader, a writer, and so on. So that's if n equals 2. This is the pattern we have. We have 2 readers read, 1 writer writes, 2 readers read, 1 writer writes. So because there's only one writer that writes at a time, the logic's a little bit simpler. So we're going to start off by actually looking at them in a second. The readers have to keep track of how many have gone in a batch, so we'll talk about that as well when we get there. Something to note is that these two classes, these are thread classes, so these either extend thread or implement runnable. These are not what is ran whenever your program starts. So let's assume that main is where your program's starting. So in main, you're going to create, let's say we'll do 2 writers and 4 readers for this example. So up here, we have 4 reader threads and 2 writer threads. They get forked from main. Whenever a thread gets forked and is started to run, it'll come into its public void run method. You see we've got both of those in both of these classes, and execute the code here. So for the writers and readers, we have something very important up here, and that's these 2 shared semaphores. So in main, wherever we initialize these threads, we would want to create these 2 semaphores and pass them to readers and writers so that everybody can share them. So you can pass them as a static variable in writers and readers. Just make sure that every instance has access to these 2 semaphores, not copies of them, the actual access to the semaphores themselves. So we have one for R control and one for W control, reader control and writer control. You'll see we started off reader control at 2 permits and writer control at 0. So in the little visualization here, I'll start reader control at 2, writer at 0. And then the only other main thing we have is class writer doesn't have any of its variables on its own, but reader does have these 2. These are static variables, so there's just one copy of them shared between all instances of reader. So all 4 of these reader threads that were forked will be able to access these 2. The first one is a semaphore called count mutex. It's a binary semaphore, so just 1 permit. The reason being is that we want to protect this static int read count. We don't want more than 1 thread to look at that at a time, so we have the count mutex so that we can access it in a mutually exclusive way. So that's important as well. You see count mutex is 1, so let me go ahead and add 1 permit to this. So the way this visualization works is these threads have just been forked from main, and they're now in their run methods, and these are the things they're trying to go down and execute lines of their code, just like they're trying to go down and get to this buffer. So we'll start off with the writers because they're a bit simpler. So whenever you fork these from main, we've created 2 writer threads that will both be running this code here. And the first thing that happens in this code is we say while true, so some sort of looping condition. The first line we have is wcontrol.acquire. So these threads are trying to acquire a permit from wcontrol, which we made earlier up here from main and we shared with the writers class. So since wcontrol has 0 permits, all these writers do when they start running, they will get to this line and they will be put to sleep and wait for a permit to be offered up from wcontrol. Because there are no permits right now, they just sit at this line and that's all they're going to be doing. So they're just going to sit outside of this barrier. So in the readers, however, remember we started R control off to 2. And if you look in the readers class, we also have some sort of loop while true. The first thing that we do here is we acquire a permit from R control. So there are 4 reader threads that we forked from main, and all 4 of them are going to be trying to acquire R control. And we started R control with 2 permits. So that means that just based on what the scheduler lets which thread run first, one of them will be able to get a permit and continue executing code. So that makes this have one permit. And then another one, just randomly selected by the scheduler, will be able to grab this and set it to have 0 permits now. So that means that two of these four reader threads were able to acquire one of the 2 permits to our control. So they got into here, they're reading in the buffer, having a good time, but 2 of them are put to sleep because there's no permits left on our control. Just like the W control, the 2 writers are put to sleep since there's nothing to acquire here yet. They just wait. 2 readers will be doing the same. 2 readers made it past, got into the buffer. So let's see what they do next. Read from the buffer. Cool. So for this, you don't have to actually read anything. You can just do a yield to simulate the read latency, but you don't need to actually affect or change any sort of data. The important thing that happens next is, so we read from the buffer, and we know that our pattern down here is 2 readers, 1 writer, 2 readers, 1 writer. So we need to figure out a way that we can know that these 2 readers have finished and let 1 writer go. But how do we do that? Well, let's look at the code. So to keep track of how many readers are finished, we use those 2 variables up here, the count mutex and read count. We use these 2. Read count will signify how many have finished their readings, and count mutex is a binary semaphore to make sure that only 1 thread accesses read count at a time. So to do that, we first have to acquire the count mutex permit. So let's say just the processor has decided, or the scheduler has decided, that reader 0 is the one that gets to this line first. So remember, these 2 just read from the buffer. They finished their reading. One of them is going to get here first and say count mutex.acquire. So count mutex only has 1 permit since it's a mutual exclusive mutex. That's the name. So whenever we grab this one, we're going to set it to 0. And let's say reader 0 was the one that grabbed that permit. So reader 0 got through here. So reader 3 is waiting right here. Reader 1 and 2 are waiting up here still. And reader 0 is executing all of this code. So reader 0 got the mutex, and we increment read count by 1. So let's go to our read count up here. I'll set this from 0. Read count is now 1, and this count mutex now has 0 permits. Down here, 0 permits. So after incrementing read count, we know that we're done with our job, but we need to see if all the readers from this in batch are done with their job. The way that we can do that is our next lines here, that this reader that made it past the mutex, he's still got the permit. We need to check if this is the last reader. So what we do, since we know our batch is 1, 2 readers, we can check if read count is equal to 2. This will tell us, say if read count is equal to 2, this will tell us that all the readers have finished and we can let control go back to the writers. For this thread, this first one, reader 0 that's down here, reader 0 is going to see if 1 is equal to 2, that's false. So we're going to pass up all of this, and our next move is to release the count mutex, and we call count mutex.release. After this, you'll notice that we're in this while loop. So reader 0 will go back up to here and try to acquire a permit to our control. So let's see visually what that looks like. We've released 1 permit back to count mutex since we're done looking at the read count variable. And this thread will come back up and wait for a permit to our control. Okay, so now that was reader 0 that just finished all of this. And if you remember, reader 3 was stuck waiting for a mutex or a permit for the mutex right here, which now that reader 0 is done, we have one. So this one will take their permit. Oops, sorry about that. Take their permit, moves on. So now we have reader 3 is executing all of this code. And now reader 0, 1, and 2 are stuck up here. So the next thing that's going to happen is, oopsies, Next thing that's going to happen is, so reader 3 down here just got the count mutex. Finish this line. We're going to increment read count as well. So that goes from 0, read count goes from 1 to 2. This is still at 0 permits. And we then check if read count is equal to 2. It is. So we need to reset the read count for the next batch. Set that to 0. So from 2, we'll set it to 0. And then this is the important part. Pass control to the writers. And we call wcontrol.release. So if you remember from the beginning, these two semaphores up here, rcontrol and wcontrol, they're shared between these two classes. So both classes can access them. And what's going on here is we're releasing a permit to wcontrol, which is going to change this semaphore here from 0 permits to 1. And then all we do is we release this count mutex, so this goes back up. So this goes back up to 1, and this reader goes back into the while loop, comes all the way back up, tries to acquire a permit. So now in the writers, we have 1 permit here, which means that the writers that have been waiting since the start of the program, one of them can finally get through. So just as an example, let's say writer 0 is the one that gets to go through. It will take this 1 lone permit, and the next thing that the writers do is write to the buffer. So say it just, does some writing, and then it's finished. So it finishes that code, it keeps moving down, and you'll see the next thing that the writer does, the next thing that the writer does is let 2 more readers go. So we say rcontrol.release, rcontrol.release. Then we also loop back up to try to acquire a permit from wcontrol. So we'll go up here and sit, because there are no permits. But the last thing we did was release 2 permits to rcontrol, which means this now has 2 permits, and we're back to where we started basically. We're gonna have 2 readers get through here, make this 0 permits so that these 2 get stuck, reading, get the mutex on the count, make this 0, make its way through, do its stuff, release this permit, back up to the top, so on and so forth. And when this second one comes through, it'll release another permit to wcontrol. So this way you can see how we pass control back and forth between the two. And this pattern of 2 readers, 1 writer, 2 readers, 1 writer, this will just repeat indefinitely since I just have while true as the conditions. But your condition would be something like while there are readers or writers left, or any other edge cases you might have to encounter. I hope this helped. If it didn't, let me know and I can try to help out some more, maybe using something less visual and we can just talk through more code. But this, I figured this might be a good idea, might be able to help some people see what's actually going on and why these threads stop and how we can make them stop. And if you got this, it should be pretty easy to generalize from n equals n instead of just n equals 2. So you could have n readers, 1 writer, n readers, 1 writer. If you have any questions about this, reach out to me or Jonathan. We'll be happy to help you guys with it. And the next thing we're going to go over is just the command line arguments, so that will be right next. The last thing we'll talk about is getting command line arguments into your Java program. And the way that we can do that is, if you note that every Java program starts with the public static void main function, and this will be your entry point to your Java program. This function has always had an array of strings called args as a parameter, and you may or may not have used it already in your time coding here, but these are actually where the command line arguments are stored. And so all I'm doing in this little code is printing out for each index in the args array, I'm just printing out what's stored in there. So if I run this now with nothing changed, we see nothing happens at all. What we can do, this is specifically, I'm using IntelliJ, which you can get with your school email. You can set a run configuration. So if I come up here, I can hit edit configurations, add new application. I'll just name it testing args. Choose your SDK. You choose what's the main class of your program so that we know where to look for this public static void main method. And then right under here, you'll see we have a text box where we can enter our program arguments. So if I type in hi there, for example, apply that, hit OK, you'll see now we're not just running current file, we're running this configuration we've set called testing args, and I put in hi there as the command line arguments. So we'll see what happens whenever we print all of these out right now. And you see that it doesn't print character by character, but it actually prints into full words. They're divided by spaces, each index of this args array. So using that, for this project, we want you to do something like -a, and then, for example, 1, 2, or 3 can apply. And if you run this, you see that index 0 of the args array is -a, and index 1 is 1. So using that, you can have some logic to check if the user entered proper command line arguments, and if so, you can go to the different problems that we have and start running the different simulations based on whether it's -a, 1, 2, or 3. So that's about how you do it in Java. If you have any questions about C or C++, please reach out. It's fairly similar with an array that contains the arguments, but we'll be happy to help out if anyone struggles with that. And good luck on your project.